Good afternoon, my name is Mark Doley, and today I'm going to present deflection in beams. And I'm going to start out by taking you back to what we learned from pure bending, because the equations that you need to derive for the deflection of beams are derived out of the equations from pure bending. And so to recall from pure bending analysis, we drew this diagram where we designated our radius of curvature. We have our beam right here and it's bending, and if it formed a full circle, it would go all the way around with a certain radius of curvature, which goes to the center of the beam, which is L sub naught. It's the original length of the beam, and that stays the same at the neutral axis. And then we also noticed that at any distance from the neutral axis, there's going to be some deformation in the beam, and that deformation is going to be it's going to be the original length if we're going up minus L prime, which is the new length, whatever that is. It depends on the distance from the neutral axis y. And so we'll recall that from our definition of arc, our length S is going to equal the angle times the radius. And so we have our original length times our angle theta times our radius of curvature. And we have our L prime is going to then equal the same angle, but our radius is going to be the radius of curvature minus some distance y from the neutral axis. And so we find our deformation comes out to theta y. And we'll also recall that our strain is equal to the deformation over the original length. And when we substitute in the values that we just obtained from our deformation theta y over our original length, which is theta times the radius of curvature, our angles cancel out, and we get that strain is going to equal y over the radius of curvature. And now a little bit more algebra. We'll bring it over. Oops. This doesn't have to be y max. It can be any y, any distance from the neutral axis. And so our strain is y over the radius of curvature. Our strain is also equal to stress over the modulus of elasticity. And our stress, you recall from pure bending, our stress is going to equal the moment times distance from the neutral axis divided by our moment of inertia. And so when we make our substitutions, we substitute this in for our stress, and we substitute this in for our strain, and we come out with the radius of curvature is going to equal the modulus of elasticity times moment of inertia over the moment. And now we bring this equation in from I learned this in calculus 3. It would take me some time to go ahead and derive this. It's very difficult. Well, it's not so difficult, it just takes a long time. And, 1 over the radius of curvature is going to equal the second derivative of our elastic curve. Our elastic curve is y of x, basically. It's going to be this line right here. Whatever, we're trying to develop an equation for that line. So the second derivative, since you weren't able to see this, I'm going to repeat it. So our equation brought in from calculus for the radius of curvature of any line, of any curve, is the derivative of the curve the second derivative of the curve over 1 plus the derivative squared to the 3 over 2 power. And now we're going to focus in on the denominator here, and it looks kind of complicated, but we're going to simplify this real quick. And we do that because for an elastic curve, y of x, which is this curve right here, the slope dy over dx is approximately 0. So this angle here, we call that the slope because by a small angle approximation, the tangent of the angle theta is approximately theta when measured in radians. And so if we use the Pythagorean theorem, we see that, or not Pythagorean theorem, sorry. If we draw a right triangle, we see that the slope dy dx is the tangent of theta. And since the tangent of theta is theta, dy dx is theta, dy dx is the slope, so the slope is theta. So the slope is approximately 0. So when we look at this, and if we plug in 0 here, we see that our denominator goes to 1. So actually our denominator is out when we're dealing, only when we're dealing with elastic curves. And so it simplifies our equation. We have 1 over the radius of curvature equals the second derivative. And we also know what the radius of curvature equals from equation number 4 here. Radius of curvature equals modulus of elasticity times inertia over the moment. And if we take the inverse of this and we flip it upside down, we can say that the second derivative equals the moment over modulus of elasticity times inertia. And that's just substituting 1 over r of k. And so I already explained this graph a little bit, but it could use some further explanation. So we have a load coming down on a beam, and it's bending the beam in some way. Obviously, we have supports at, we call this A and this B, and depending on where these supports are, this curve is going to be different. Depending on how much the load is, this curve is going to be different. So there's a lot of variables involved, and I'm going to go through how to determine what that equation is. But with the deflection of beams, basically we're trying to find the slope at any point along this curve, which is theta of x, of curve y of x, and we're also trying to find y of x